Hello. In this video, I will try to talk about one of the limit that includes trigonometric function. The limit looks like that. Limit as x goes to 0, function sine x over x is equal to 1. Okay? That means this, I can say this is a property, and I will try to prove it, and then we will try to compute more complex functions, but still involving that property. That means sine of x over x, if x is 0, the limit is always 1. The behavior of this function is 1. That means, let's prove it first. I will take a circle like this one, and we can notice this triangle, and we can also notice the small triangle. Okay, that means let's see something. I will color a few things. First of all, I have this green triangle, okay? Let me add this circle, I can call a unit circle. Radius is 1. Okay? I don't know if I can write this down. Radius is 1. That's radius. Okay, that means I do have a green triangle. Then in the center, in the middle, I do have a purple part, which is just the sector of the circle. And then I have a little bit greater triangle. That means one thing is obvious, that the green area, it's less or equal to, eventually, than the middle one, and the middle one, the purple one, is less than the blue one. Okay. Now let's define the areas. That means the first one will be defined like 1/2 r sine theta. But let's see, we need a few things, theta and height. That means the area of the triangle, it's 1/2, I can possibly write, base times height. Okay? That means 1/2 base is radius. That means I will probably put 1 in a minute, but I put r. And height, if I will compute sine theta will be h over radius, this one, hypotenuse. Since radius is 1, is just sine theta. That means height is sine theta, b, the base, is r. Okay, I will put in a minute 1. Okay, in the middle part is just the area of the sector of the circle, 1/2 radius squared theta. That's the formula. Of course, this is theta. And the big triangle, okay, we need also 1/2 times base, which is radius, and times height. But in this case, if this is theta, my height could be defined as a tangent theta. Okay, and let me put the same formulas, but of course, substituting r equals to 1. Okay, each of the parts contains 1/2. I should keep my relation, of course, less than. I am dividing each part by half. The half is gone. Okay, and now what I will do, I will divide each part by theta. Okay, I mean sine theta. Sine theta, theta over sine theta, tangent theta over sine theta. Okay. Okay, and what we have? This is 1. This will stay like it is. Tangent theta is sine theta over cosine theta. Canceling sine theta, we're getting 1 over cosine. Okay, that means I am gonna take this, the last inequalities, compound inequalities, and I will reverse. I will reverse the direction of the inequality, and this will force me to switch the fraction. This will be 1/1, of course 1. This will be sine theta over theta, and this will be cosine theta over 1. Okay. 1 sine theta over theta, cosine theta over 1, which is just cosine, and we can see the directions change. And now what we can do, we can try to check using the squeeze theorem, we can try to check a limit. That means limit as theta goes to 0 of 1, limit as theta goes to 0 of cosine theta, and the middle part. Excuse me. Okay, and of course, limit of the constant is just constant, 1. Cosine at 0 is 1. And we can nicely see, based on the squeeze theorem, theorem, if both of the limits on the edge are the same, the middle part is forced to have the same limit. That means this limit sine theta over theta, if theta goes to 0, the limit is 1. Okay, that means this is really nice proof. Now, of course, we don't really have to, I mean, it's nice to know the proof, but we don't have to really like redo it. I want you to know this property and apply. Okay, let's see the summary page. Sine of x over x, if x goes to 0, is 1. I can also flip a number, I mean flip a function. I can say x over sine of x, it's also 1. And another function, another trigonometric function that will also hold this property is tangent. But it's just because tangent, behind tangent of x, we do have sine of x. That means tangent of x is sine of x over cosine of x. If I will copy x from the denominator, I still see sine of x over x, 1. And cosine at 0, it's 1. Okay. That means tangent of x over x, and of course the reciprocal. That means these four are the formulas that we should know. Of course, this is true, which was just proven, and we can apply. So now let's solve a few limits. Okay. Limit as x goes to 0, sine of 2x over x. Okay, that looks like sine of 0 over 0, but what we have to see identical input. That means since I have 2x, I really have to see 2x in the denominator. Okay, that means what I will do, I will multiply denominator by 2, but since I am multiplying denominator, I will multiply numerator too, because I can cancel out these two blue 2's. Okay, I can simplify, cancel out, and still have my original function. But of course, I will not cancel out. I will keep it. And now this is my property. Sine of 2x over exactly the same quantity, 2x. This quantity, this limit, as x is 0, this goes to 1. Okay, and then outside the box, 2 stays, and this is the answer, 2. Okay, I did type this for you. We can see my blue, additional blue 2, and I can just copy for you one more time. This is sine of 2x over 2x. This quantity must be the same. In order to use the property, the red circles, they have to be the same. Okay, and my green box is 1. The final answer, of course, is 2. Yeah, that means I did use my property. Okay, limit number 2. Sine of 4x over 3x as x goes to 0. Okay, that means I see sine of 4x, and I don't really have 4x. Okay, that means I will multiply by 4 and multiply by 4 the denominator, the numerator and denominator. And now I see sine of that quantity over the same quantity. This is my property. This is 1. Sine of 4x over 4x. Because I can't say sine of 4x over x is 1. No, I have to have identical 0. 4x, 4x. Okay, this is 1. What's left outside the green loop? 4 over 3. Okay, and we can see I can just make, it's the same thing. I'm just kind of repeating for you that you will master your skills. Okay, sine of 8x over sine of 5x as x goes to 0. Okay, that's what we're missing. We're completely missing 8x in the denominator and 5x on the top. That's mean what I will do. Let's see what I did. This is my original function, sine of 8x over sine of 5x. And I multiply and divide by 8x, which of course I can simplify and it's gone. And I multiply and divide by 5x, which if I will cancel out, I have my original function. That means doing this stuff, this multiplication and division, I didn't change an original function. Okay, but now let's take a green color because that's our property. And let's see. I see sine of 8x over 8x. Perfect, that's one. And I also see the reciprocal, but this works, 5x over sine of 5x. This is also one. Okay, that we can see the blue, I use the red color, but the green loop and the blue loop is my property. And we can see 8x, 8x, 5x, 5x. Then I am allowed to use the property, and this is 1. And what stays outside? 8x over 5x, of course, is 8 over 5. The x is gone. We should still have a limit, but okay. Example number 4. Okay, limit as x goes to 0, x times cosine of 4x over sine of 8x. Okay. We have to be really careful because cosine of 4x doesn't really hold this identity. And actually, cosine of 4x, x is 0. If I will put 0, I have 4 times 0 is 0. That means cosine at 0 is simply 1. That means if we have product, we can kind of ignore it, but I will still keep it. This is 1, that we don't have to really divide. But what I see, my sine of 8x, and on the top would be nice to see 8. That means I will multiply and divide by 8. Okay, we can see the additional 8 and 8. And now I see my property, sine of 8x over 8x, but the reciprocal, upside down. This is 1. And what stays? Cosine of 4x, that we just talk about this. This will be cosine at 0, it's 1. 1 over 8, because 1, 8 in the denominator was outside the loop. It's not 1, it's outside. Okay, example number 5. Okay, limit as x goes to 0, sine of 2x cubed over x cubed. Okay, that means some multiplicity is added. Yeah, it looks a little bit complex, but the good thing is the power cube and cube is exactly the same in the denominator and numerator. That means I can take that cube and put outside. Okay, that means I have my function sine of 2x cubed and x cubed. Okay, and now I believe that we can really take care of the limit inside of the inner function. Because what we have sine of 2x over x. We're missing 2 in order to use the property 2 and 2. And I will loop my property sine of 2x over x. This is 1. 1 cube is 1, but what stays? 2 stays outside. That means 2, and still remember about the cube, the outer function, 2 cube. Oh, I didn't write the answer. Of course, we know that is 8. Okay, similar thing. Limit as x goes to 0 of the function x squared sine 4x squared. I will do exactly the same thing. I will put the square outside, and I will take care of the limit inside. Sine of 4x and x on the top. That's mean what I'm missing? 4. 4 and 4. Please remember, we have to put on the top and the bottom. Now I will loop my property, 4x over sine of 4x. This is 1. I can't use the property if this will be not 4. Okay, 1. That means 1 squared is 1, and 1/4 squared, of course, is 1 over 60. Okay, example number 7. Sine of x over tangent of 7x as x goes to 0. Okay, that means we know that this property is good for sine of x over x and tangent of x over x, or the reciprocals. That means I'm missing x in the denominator and I'm missing 7x on the numerator. In order to loop it, say it that is 1, basically applying the property. That means what I need x and x. Oh, okay, I did multiply everything by 7x because I don't have to double x, which I will cancel out anyway. That means I have my original limit. We can see sine of x, tan 7x, the same thing. And I multiply by 7x and divide by 7x. Okay, because For the sine, I only need x. For tangent, I need 7x in order to say that this is 1. That means I will use this. Okay. Okay, I can't do different actually because tangent is maybe. Oh no, this will also not. Okay, that means sine of x over x is 1. And the other property, tangent 7x, and I need, okay, I will kind of cross. The red loop is also 1. Because 7x over tangent 7x is 1, sine of x over x is 1. And what stays? 7 is outside, in the denominator 1, 7. Okay. Example number 8. Sine of x squared. Okay, now not function sine is not squared, it's just the quantity, the input, the argument is x squared over x as x goes to 0. If I want to apply this limit, sine of x over x, if x is 0, the limit is 1, then what I have to see? I have sine of x squared. That means would be really good to see x squared in the denominator. Okay, I will multiply the numerator and denominator by x. And then I see sine of x squared over x squared, because this is, of course, x squared. Right? That means this limit is sine of x squared over x squared if x is 0, identical argument, identical value in the denominator, this is 1. And what stays? Actually, x stays, and x is 0, it is 0. That means this is actually a good example. Of course, we use the property, but this is also showing me that the original limit, whatever form it has, like it's trigonometric, but original limit has the form 0 over 0. And probably watching my videos and listening my explanation of limits, I was mentioning a few times that if we have a limit and we're getting 0 over 0 by direct substitution, most likely the answer is not 0. Okay? But we can see this is the one exemption. I mean, we do have few, but this is the exemption that is 0. And we can also see I really simplify my limit, and the important thing is I did cancel out the 0 from the denominator. We can see I don't have denominator, and what is most important, I don't have 0 in the denominator. If we have 0 in the denominator, we have to be always really careful to say, oh, the limit is 0. No, I mean 0 like a small number, because this is not safe. Okay? And probably you can notice we kind of have it like double 0, like x squared, and only one x. That means I did cancel out, I managed to cancel out one of the x, but I didn't cancel another, like additional one, which actually I play with. Okay? That means we can see could be 0, but I really have a strong reason. Example number 9. X times cotangent x. Oh, interesting. As x goes to 0. X is 0, cotangent at 0. What's the value of cotangent at 0? I think cotangent at 0 is undefined, right? Because cotangent is cosine of x over sine of x, and sine at 0, of course, is 0, but placing sine in the denominator will give me like undefined value. That's in cotangent is not defined at 0. Cotangent has an asymptote. Okay, but I actually, yes, explaining this, I did rewrite function cotangent in terms of sine and cosine, and now we can nicely see what is the limit. That's me using green. X over sine of x, easy. We don't even have to play with the coefficient. This is 1. And what stays? Oh, I do have the final answer, but we can see substituting 0, we have cosine at 0 degree, and cosine at 0 is 1. Okay, this will lead to the cosine at 0. Cosine is nice. At 0 is 1, but we're kind of safe with cosine function in this type of expressions. Example number 10. Oh, really nice exam type question. Limit as x approaches 1. Okay, a little bit different. And then sine of x minus 1 over x squared plus x minus 2. Let's use direct substitution. Substituting 1, I have 1 minus 1, sine at 0. 1 minus 1 is 0. Okay? That means I kind of have sine at 0, and substituting 1 in the denominator, 1 plus 1 minus 2 is 0. That means it looks like sine at 0 over 0, which must be 1, but what I have to do, I have to really see the identical 0, because this is 0, it's good. I will still use my property, we can see sine at 0 over 0, but what I have to make sure, I have to make sure that this 0 is identical like this. And we can see at the moment it's not, because this 0 on the top is x minus 1. Of course, as x is 1. And then in the denominator, I don't have just x minus 1. I have x squared plus x minus 2. But what I have to do, I have to find out in between x minus 1. Probably I have to factor out. Before I do this, one more comment. Please note that the limit, the x, doesn't go to 0. And this doesn't matter. This could be any number. But what is important? Important is this quantity. This quantity must be 0. Sine of 0. Okay. Of course, I did factor out denominator, x minus 1, x plus 2. We know how to factor out. And now I can nicely see identical value. X minus 1, x minus 1. That's identical 0. This is my property. Sine of 0 over 0. Sine of x minus 1 is 0 if x is 1 over x minus 1. Okay, and what stays? X plus 2, 1 plus 2, 3. Okay, 1/3. Example number 11. Limit as x goes to 0, sine of x over x plus tangent of x. Interesting. That means what we will do, still is 0 over 0, all right? Sine of 0 is 0, x 0, 0 plus tangent of 0, 0, 0 over 0. That means this one looks a little bit different because suddenly I have like expanded form addition. But what I will do, I will just take a risk, I can say, since we're talking about the limit, sine of x over x as x goes to 0 is 1, I will try to create that limit in this expression, which means I will take each term, sine of x, x, and tangent of x, and I can like multiply by something, or I can divide, I can change this. That means I will divide each of this term by x. Sine of x over x over x, tan x over x. Because I can multiply and divide the denominator and numerator by the same number, the same expression. I'm not changing anything. Okay, and now we can nicely see sine of x over x as x is 0, this is 1. This is 1 also, and this is 1. 1 plus 1, 2, 1/2. And example number 12. Actually, almost the same like example number 11, just additional coefficients. That means I will do the same. I will take sine of 3x divided by x, 4x divided by x, and tan 2x divided by x. And we can see this is 4. This one, we will need additional 3 because we have sine of 3x and we need 3x. And now, since I have this 3x in the denominator, I can loop it. That means this is 1, but what stays? 3 outside. And the same for this one, tangent of 2x over 2x. Then I can use the property. This is 1. That means what stays? 3 on the top, 4 plus 2 in the denominator. 3 over 6, 1/2. Okay. And I believe this is all of my examples for the property sine of x over x as x goes to 0, that is 1. I do have one more limit, but it's a little bit different. It's trigonometric limit, but we can see it's not, sine is not 0. This this is fine. This is still okay. We may have x approaches different value. This is pi over 4. But in order to think that I might use the property, I should really see this somewhere inside this expression. That means sine of, if x is pi over 4 minus pi over 4 is 0. Then I will think, oh, probably I have to find the same quantity somewhere, somehow. And if x goes to pi over 4, this limit is 1. Okay, we can nicely see this. But I will erase this, and we have totally different thing. Let's try to do direct substitution. Tangent at 45 is 1. 1 minus 1 is 0. Sine at 45 and cosine at 45 has the same value, root 2 over 2. If I subtract, I got 0. That means actually I have just my standard limit 0 over 0. This means that for 45 pi over 4, I do have a common factor. I have to rewrite this expression and find this common factor. That means the only thing that I can see tangent of x that I can rewrite as a sine over cosine. Okay, we can see. Now I can get a common denominator. Oh, actually, I kind of jump. Or the other way is, I can do for you the common denominator. I can rewrite actually 1 as a cosine of x over cosine of x minus sine of x over cosine of x. Yeah, this is just this. And then cosine of x minus sine of x, I can rewrite on the common fraction bar. And we can see cosine of x minus sine of x over cosine of x and copy the original denominator. Great. Now I see almost the same factor, sine x minus cosine x and cosine minus sine. I switch the order and pull out the negative in front. That means now the common 0 is gone. Now I can simply substitute 45. And I think you can use the unit circle and get this answer. Because cosine at pi over 4 could be actually rewrite like that, or square root of 2 over 2. But we can say 1 over root 2, we flip that, square root of 2, of course negative, we will copy from the numerator. Okay. Thank you very much. That's me now. This was the additional thing to the section, to the derivatives of the trigonometric function, because limits are also important, of course, the main concept of calculus. Thank you.